Thanks, Hassan. That was an awesome presentation, and one I know a lot of people here got a lot of great information about a really tough topic when it comes to actually getting buy-in about using mathematical optimization to solve problems. Communicating the benefits of mathematical optimization was something that was difficult for me early in my career, so I hope that session was super informative for all of you out there. Now let's change gears to talk about something that's been requested fairly often in the Optimization for Data Science series, and that's handling uncertainty in mathematical optimization. This topic can be very challenging to tackle and one that you sort of need to maybe tread a little lightly on sometimes, but it is very relevant and one that everyone should be aware of when it comes to, again, getting buy-in about projects because it's something that you're going to be asked about. So in this session, we're going to explore some practical approaches to incorporating uncertainty into our optimization models. So these methods won't necessarily be the first to pop up in a Google search or the first thing that ChatGPT is going to recommend when you ask how to solve such problems. And we'll get into why in a little bit. These are meant to be things that you can do that are a bit easier to implement but can still provide tremendous value when used with mathematical optimization. So let's dive into what we're going to talk about. So the agenda for this session, first, we're going to talk about, is addressing uncertainty important? You probably know the answer to that, but he'll hit on that very quickly. After that, we're going to set the stage. So talk about some of the common approaches that you'll see when you use Google searches or when you ask ChatGPT or when you sort of just go out there and sort of say, hey, I want to solve optimization problems that have uncertainty in it. What should I do? We'll sort of talk about the things that pop up first. But then after that, we'll sort of talk about some other prerequisites that that are important to talk about when we start talking about uncertainty and likelihoods and things of that nature. And then here are three practical approaches that we're going to talk about. Again, these are things that are typically pretty easy to implement and still provide a lot of really good information and value. So first is simulation over solutions. Then we're going to dive into some individual chance constraints. And then we're going to talk about scenario optimization. So we'll define each of those, what they do, and sort of how to implement them fairly quickly. What if? This is an important question that you'll undoubtedly be asked when working on projects. But it is one question that mathematical optimization can answer actually very, very well. Mathematical optimization is a great tool at being extremely flexible way to model problems. And we've seen this time and time again with how we're easily able to change objectives, add variables, take out variables, add constraints, take out constraints, and so on. When it comes to uncertainty, we've even started to explore this in Opti 201, even though I really didn't mention it at the time, but we'll get to that in a minute. So to answer the question, yes, of course it's important, but there's a but. While uncertainty is everywhere, we know that, and optimization is also everywhere. We've also just learned that a bit earlier yesterday. There are reasons why directly handling uncertainty in mathematical optimization isn't really quite as widespread as you think. So we already actually discussed a couple of ways to deal with an uncertain future back in Opti 201. So the first is using multiple scenarios, and hopefully this rings a bell. And I'll discuss the difference between multiple scenarios and scenario optimization that I just talked about. But so as a quick reminder, running multiple scenarios is a great way to see how solutions change maybe under new circumstances. So maybe your objective changes, or the objective coefficients change, or your bounds on your variables change, or other constants maybe change. But what you can do is you can solve for each of these distinct scenarios. If you use the Gurobi API, it's done much more efficiently, but you have distinct scenarios and you can have a playbook ready to go for each. And this is mainly useful if you have ample time to prepare and make adjustments. So if I know that scenario one is coming and I have time to implement the results of scenario one that I get from the optimization, then that's great. Awesome. I have plenty of time to do it. But what if that's not the case? And that's typically not going to be the case. Then that's when these other methods are going to be useful. So the other topic from Opti 201 is that we discussed is things like mini max or maxi min. You can think of this as a quick way to sort of optimize worst case scenarios. So say, for example, you want to minimize the maximum distance that you travel. Well, this will make sure that you're guaranteed a no worse than type of outcome, which can be very useful in certain situations. So now let's set the stage for handling uncertainty in optimization. So first, what we're going to do is we'll talk about some of the common approaches that you'll see if you were trying to research this topic and seeing what exists out there in the wild on the internet. Let's say that you have an optimization problem and you want to figure out how to add uncertainty. Someone's saying you got to add uncertainty or you think you need to. And you fire up your favorite search engine, open up ChatGPT or some other service like that, and you say, I want to do uncertainty and optimization. All right. Essentially, there's going to be two things that pop up first. First is stochastic programming, and then the second is robust optimization. Each of these have their use cases, their pros, their cons, and things like that. Stochastic programming is, and particularly multi-stage, is something that considers multiple stages in which you're able to sort of realize the uncertainty that sort of realize what happened and then make adjustments and make different sets of choices. Robust optimization is something more along the lines of kind of like the maxi-min that I was talking about before, where you're optimizing against like sort of like a worst case scenario, but it's much more complicated than that. And because they're both pretty complicated, we're not going to dive too much into them, but I wanted to at least put the names out there because, again, if you search for this, this is the first thing that is going to pop up pretty much each and every time. But there are challenges in adoption for each of these. You might be wondering, well, again, uncertainties everywhere, optimization everywhere. These are the common things that I see first. Why aren't these things sort of used all the time? Well, there's definitely some challenges there. And one is, the complexity of the models themselves. Once you say, I'm going to do multi-stage optimization, robust optimization, those types of models and what you need to do are quite complex. And when you make models more complex, you run into scalability issues. So if you're trying to do this for a very large problem, you might be running into some issues there. Another reason is that there may be a lot of additional information needed for multi-stage optimization. You need multiple sets of more information. For robust optimization, you need to understand a lot more about the uncertainty sort of region in a sense of your problem, and there may not be data to support this. You may just be, if you don't have the correct data, garbage in, garbage out sort of thing. So that's another reason why you may not be doing one of these approaches. And then I think probably the most important one is if you're really willing to accept a much larger mathematical optimization problem, then you're typically better off doing something along the lines of making your current problem just much more realistic. There's always granularity that you can add to your problem, more or less. And if you're willing to accept a much more larger problem, then you're probably going to say, oh well, instead of solving something weekly, let me solve it daily, or instead of solving daily, maybe it's hourly. There's always ways that you can improve your optimization model by adding more variables and more constraints to it. So if you're willing to accept that, then that's probably the way to go in as opposed to adding in that uncertainty element. So now let's talk about some of the other prerequisites for what we're going to talk about the rest of the time in this session. So one is probability. I would assume that a lot of you have had some exposure, maybe a lot of exposure to probability theory, statistics, things of that nature. but I just wanted to make sure I cover a couple things that I won't really necessarily hit on, I think, in this presentation per se. It will be in the modeling exercises a little bit, but just some things I want you to sort of have in the front of your mind when we sort of go over some of these techniques and you're doing some of the exercises in a little bit. So one is when it comes to probability, the types of random variables. And a random variable is essentially an outcome that we don't know yet. And there are two main types of random variables. One is discrete and the other is continuous. And given the fact that we have sort of discrete decision variables and continuous decision variables, I think, it is pretty analogous, what the difference is between each of those. Discrete random variable takes things like a fixed number of outcomes per se. There could be an infinite number, but it's but there's a set of 0, 1, 2, 3, so on and so forth can be your outcomes as well. So a quick example of like a go-to discrete random variable is you flip a coin, heads or tails, two options. You either get heads or you either get tails. Rolling a 6-sided die, one of 6 outcomes. Rolling a 20-sided die, one of 20 outcomes. So those are a couple examples of discrete random variables, but there's also some that you've probably come across. I'll mention a few by name. One is, and essentially the ones that I just sort of talked about are what we would call uniform discrete, where each of those outcomes are equally likely or supposed to be equally likely. But there are other ones, if you're familiar with something called the geometric distribution, or the binomial distribution, a Poisson distribution. Those are a couple discrete ones that are pretty well known. The continuous, as you think about what a continuous decision variable is, continuous random variable is a random variable that has a infinite number of outcomes per se, but probably bounded in some cases, sometimes not. But the good old normal distribution, Gaussian distribution, that's sort of like the go-to example. So a couple terms that could be useful when trying to incorporate some uncertainty into optimization is what we call something called a probability mass or density function. So in the discrete case, that is the probability mass function is something that gives the probability of a random variable taking a certain value. So I roll my 6-sided die. What's the probability I get exactly a 3? That is something that the mass function gives. And in the continuous case, that function is if you take the area under that curve from a particular range, that gives you the probability of the random variable sort of falling between those bounds. But the little more important one, and it's the cumulative density function, or the CDF. It's related to the mass function or density function, but that tells you the probability that your random variable x, in this case that we have up here, is going to be less than or equal to some certain value, which you can really easily say what's the probability that x is greater than a particular value by taking 1 minus that. So this is a function that's very important. And then the other topic is something that we call expected value. And this is essentially something you can think of as an average, particularly a long run average. And in the discrete random variable case, it's quite easy to compute. Well, it's not too bad to compute in the continuous case all the time. Sometimes it is. But in the discrete case, it's very easy. It's the value that you attain times the probability that you get that value. Sum it up across all values. So these are a couple things about probability that I think we want to talk about to set the stage. And then the other one is simulation. I talked about simulating over solutions a little while ago. So sort of hit on a little bit actually just a very, very, very quick introduction to Monte Carlo simulation. There are other types of simulation like discrete event, which is used to simulate sort of complex systems. But Monte Carlo simulation is just more or less just drawing samples from a known or assumed distribution, and they use that to represent the randomness. So I put a little bit of code up here to generate random samples of a normal distribution where you assume a mean, you assume a standard deviation, and you say, hey, I want this many samples. You can use a little bit of code like this to get that information, and then use that information to help you address the uncertainty in however you need to. So those are a couple things that I wanted to make sure that we sort of use to set the stage in order to help us apply these more practical approaches to incorporating uncertainty in mathematical optimization. So I talked about these practical approaches. I mentioned them already. So let's dive into the first one. So let's say you just hit optimize on a model. You have your max C transpose X subject to AX less than or equal to B. Good old linear program at this point, possibly integer if you want to add those things on as well. But so you have your model, you click optimize or hit optimize, and you have the optimal solution. We'll call that a X star. And we have the objective function value at that optimal solution. So that's C transpose X star as well. So you have that information. Great. But you know something. You know that those objective coefficients, they're not quite as stable as you're assuming at this point. Well, what you can do is just use some simulation to create a new set of simulated cost vectors. Let's call that C capital N transpose. So you have a whole bunch of new potential objective coefficients that you can look at. Well, the easy thing to do once you have all of these is let's just see the variability. Let's just see how things go for each of these objective coefficients in our set. So maybe you simulated these through and you knew the distribution, so you were able to simulate what they what the values could be, or maybe you just randomly sample them from historical values. However you get to those, you have your new set, and let's just see what the objective function value is given your fixed optimization solution, your fixed optimal solution. How does your objective change given this new set of cost vectors? So you can help understand sort of the spread that you can expect, which can be very useful in communicating sort of best cases, worst cases, average cases, things like that. Sort of what, sort of just helping you understand what to expect, given you now know that your coefficients may not be exactly what you assume them to be at the beginning. Well, you may be asking, what if other values in my problem change? Let's like say that the right-hand side of my constraints, the constant value on the other side of your inequality. Let's say that is something that we know is a little tricky and maybe not exactly what we estimated initially. This may mean that those constraints now may be violated. Again, you run your optimization, you get your solution, you have a fixed solution. Again, we're calling that X star. What given variability in B, which is sort of like your right hand side, what happens for my violated constraints? Well, understanding constraint violations is something that is done can be done directly in the modeling part, and that is typically done with something called penalty terms, with additional decision variables, but you may still want to do analysis like this using simulation to understand the spread or variability, and that's something that using a penalty term may not be able to do exactly. But so let's say we have our right hand sides, denote that with B. Let's let that B tilde IN be a simulated right hand side for a constraint I. Again, you have a set of simulations N, or a set of simulated values, be it from some known distribution or from some historical set that you're just sampling over, something along those lines. And you may be interested in understanding the number of times that, given your optimal solution, again, X star, for your particular constraint I, the number of times that this constraint is violated. Well, yeah, you can then simulate your bees, see the number of times that your constraint is violated, and that can give you something that is very useful, again, in preparation or understanding what, how good your solution may be in your eyes once you sort of see what that information is as well. And if you remember from, I think we actually did this in 101, where we talked about a constraint slack. Again, it's the difference between essentially the left-hand side and the right-hand side. It's that gap. Extracting constraint slack, and that may be useful here as well, and using simulation over that to sort of see similar information as well. So again, you can use a method like this to quickly understand, hey, how likely is it going to be that this constraint is going to be violated? That could be some very useful information for you. So the last thing that I'm going to talk about in terms of simulation with over solutions is uh, what solutions seem better? And you think, what solutions? There's one solution. Well, no, not always. Um, and this is something, again, we talked about in Opti 201. We looked at solution pools. So we were able to extract, something like the top 20 solutions or top 10 solutions, or just give me any 30 solutions. We went over several different ways to extract multiple solutions from one model when you run it. So if, let's say, you take the top N solutions or top M solutions from a particular model, certain solutions may give you better sort of statistical results, I guess, when you look at it from a simulation perspective. So let X star S be the optimal solution, S in your pool. So you have, again, a whole bunch of solutions, and you want to look at, hey, what's some of the variability there? So for example, you have C transpose X1 and C transpose X2. So these are your top two solutions, and they have a really, really close objective value. So your C transpose X for each of those is very, very, very close, but maybe the variance in the first solution is less or much less than the second solution. So maybe that is something that will help you differentiate and say, okay, yep, X1 is definitely the solution for us, or maybe this was flipped around, and maybe you're willing to sacrifice a smidge of objective function value for the better certainty and less variability that the other solution will give to you. So this could be something that is also very helpful in decision making. So again, in short, quick simulations can provide extra context to mathematical optimization solutions. So the next thing that we're going to talk about are what we call chance constraints. And these are another thing that's really simple to implement. Well, they can be. And we'll talk about which ones are simple, which ones are not so simple, and stick with the simple ones for now. But so let's move on to chance constraints. So let's talk about individual chance constraints. And again, something that we've been doing a lot in the Opti for Data Science series is, again, translating words to math. So let's start with this sentence here. I want to make sure that I meet demand for a certain product with probability of 95% or 0.95. So since we're talking about a constraint in a mathematical optimization problem, we have let's assume for now, linear inequality, sum over j, a ij times xj greater than or equal to we have b tilde I, which is that's our ith constraint, and the right-hand side is a random variable with some known distribution. Let's say, hey, maybe it's normal distribution. Well, when we take the sentence on the left and we want to apply it to the inequality on the right, we end up with a probability statement. So we want the probability that this linear inequality, with the right-hand side being a random variable, must be greater than or equal to some probability that we want. We'll kind of call it P. In this case, for the sentence, it's 0.95. So if you sort of see in the normal curve here, we want the area under the curve, more or less, to be P, So we want to find a value Q based off of the distribution of BI and the probability that we want P. And we want to take the area to the left of that to be P. So then everything else we want to squiggle out, and we want to find that value Q. So that changes our inequality from BI on the right-hand side, some constant value, to another constant value, but it's based off of the distribution of the random variable B and the probability P. So we end up with essentially a deterministic uh, inequality, but now it represents the certain probability that we want given the distribution that we assume for B. And by the way, we call that the pth quantile. So what we talked about just now is what we call an individual chance constraint. So the probability at one individual constraint meets, is satisfied, is some probability. Well, what if you're saying that's not enough for me? I need more assurance. I want to make sure all of my products, that demand for all my products is met with probability 0.95. Well, that's where things get a little bit more complex, because you're taking, all of those constraints instead of just one individual constraint. You're taking all of them. So you say you have n constraints. Well, now all of those are in the probability statement, and that gets pretty complicated to deal with, because that requires dealing with multivariate distributions, and we're not going to worry about that for now. It exists, you can do it, but it's quite complicated. So we're going to stick with the individual chance constraints for our exercises coming up. And now we're going to move on to our last topic for this session, and that is So this last topic is what we call scenario optimization, and that's something where you consider multiple scenarios simultaneously. And this is where the difference between scenario optimization and multi-scenario optimization, which maybe not the best terminology there, but that's the difference. In multi-scenario that we talked about in 201 and earlier here, we were considering and solving different scenarios separately from one another, even though we can sort of batch them together using the Gurobi API. They were still sort of separate solves in a sense. Well, in scenario optimization, we're considering a finite set of specific scenarios that each represent different possibilities, but we're considering them simultaneously. So let's assume that we have an investment portfolio problem, and we have scenario 1 is that there's faster technology sector expansion. Scenario 2 is renewable energy adoption. And scenario 3 is maybe there's healthcare policy reform. Each of these things are going to affect sort of your investment strategy. But what scenario optimization will do is it will find a solution that is feasible across all scenarios, and then give you something that should be performing pretty well given that. And I sort of am loosely saying that because, that's something that's not super guaranteed. One of the guarantees of mathematical optimization is the best solution, but when you are sort of combining scenarios like this, it gets a little bit more complicated. But essentially the way that this problem looks is you are maximizing your original objective of sort of C transpose X, some objective function, but essentially you have a set of constraints for each individual scenario. So there would be a set of constraints for scenario 1, another set of constraints for scenario 2, and another set of constraints for scenario 3. All of those would be added to the model. So the optimal solution that you would get would be something that is feasible for each scenario 1, 2, and 3, which is pretty cool to think about. So I think that is it for this section. Next up is exercise set 2. So check the app, check the website for the links to get to that, and I'll see you there.